you all know. Okay, so hopefully you've all found us all right today, and you've got working computers and all. Wonderful. Okay, so I'm gonna show you a little bit on Blackboard what I wanted to show you last week real quick, and then we'll get started with our lab for today. So in Blackboard, I've got all the content and stuff over here. Hopefully you guys have seen that already. We've got a tab right here I made for labs. So when you click on that, that brings you to this page I'm on. I've got these 3 folders. The first one is for lab resources. That's those documents I was talking about last week. So that's just general useful stuff to know. I would recommend going over all that. And then right here we have our lab examples, which are the examples I go over in lab with you guys. So I have one posted for today. And then we have lab assignments right here. And that's where the assignments that you do on your own are posted there. Any questions on that? Okay. Just real quick, we've got that document I talked about last week that was describing the background behind SAP2000 and finite element analysis programs. If you can't make it to a lab on campus, you can use SAP2000 using the virtual computer lab. So you can find those instructions here if you're unfamiliar with how to use the VCL. Some exciting news since last week. I've managed to get them to put version 22, which is the newer version on VCL as well. So you got both versions on there now. And then the basic procedure, which we talked about, the detailed procedure, these are the kind of step-by-step menu options to get to where you need to go. And then I have an example lab report here to kind of talk about what you want to make sure you're including in your lab reports for the assignments. Any questions on any of these or any of that stuff we covered last week? Wonderful. Okay, so if we go back here, let's start with our example for today. So I'll open this up. You can follow along. It's all up on Blackboard if you want. If not, it's all on the projector there. That's showing up all right. Everyone can kind of see. Everyone can hear me all right? Perfect. Okay. So we are going to be doing our first example lab today. It's going to be a 2D determinate truss. So we're going to consider the 2D determinate truss shown in figure 1, which is on our next page here. The height of the truss is given as 10 feet, and the width of each of the divisions of the truss is also 10 feet. And we're going to consider the self-weight of each of the elements in the truss to be 0. So SAP2000, it's a pretty smart program. When you have actual physical structural members in reality, they have self-weight to them. However, usually when we're doing analysis, we aren't adding in the distributed loads for the self-weight of the members because it's usually minor in comparison to the external loads. However, SAP2000 goes and adds that in automatically. So today, because we're analyzing a truss, we want to just turn that off so that it will give us something similar to what we get if we analyzed it by hand. In SAP2000 today, the units we're going to be using are pounds, feet, and Fahrenheit here. So these are the US customary units. SAP does all sorts of units. It does a lot of combinations of USCS units as well as SI units. The material we're using is steel, specifically grade A992, grade 50. So this is the material we're using. It's built into the program there, so we're not going to worry too much about this. We're going to be using steel in this class because it's a nice isotropic material that makes the analysis kind of just easy on us, and we don't have to worry about all sorts of other complicated things when you get into more complicated materials. The section property we're going to be using for each of the chords in the truss is going to be an HSS 2x2x1/4 shape here. Anyone know what HSS stands for? Different HSS. Exactly, hollow structural section. So that's basically just a box tube, hollow inside. So we have a pretty efficient section there. All the steel outside, good with torsion, good with flexure, pretty good with shear. Pretty efficient overall. And then the loads I went and showed in the figure. So let's look at this figure here. There we go. So we've got a truss like this here. We've got points A, B, C, D, and E on the bottom here, points F, G, and H on the top here. The truss is 10 feet high. Each of the 4 divisions across are 10 feet wide each. And we've got a 50-pound horizontal load on F here and a 100-pound vertical load on C right here. Also, we have a pin support at E and a roller support at A. Make sense there? Okay, so we're going to model this in the program, and it will go and give us a bunch of results. And among those results, after we perform our analysis here, I want the following deliverables, and I'll show you how to get these. We want to find the reactions for each of the supports with values and arrows. So the arrows show which direction it is, and the values give you the magnitude. We want the axial force in each of the members. We want the deformed shape of the truss, the horizontal and vertical displacements of joint H, so how much specifically that joint moves, as well as the moment diagrams for each of the members of the truss. And I'll show you how to generate all of those. Okay, any questions on the problem we're doing today? Okay then, so let's get started. If you go and look in your computer here, you will find SAP2000. It's under S here. It's in a folder here called SAP2000, and we have version 22 in the computer labs. So you can click on these, and it's this blue kind of diamond thing with an S on it here. So you can click on that. I already opened it up earlier. When you open it up, I'll give you guys a minute to do that. It'll look like this. I'm not sure. I was working with OTS over the week. They said that pretty much all the computers have it on there. They are making sure they can get it installed on the rest of them. So if it's not on there, let me know. And in the meantime, we can set you up on the VCL. Yeah. Okay, cool. Yeah, so they're working on getting it onto all the physical machines in the labs that are supposed to have it. They're almost done with that, so it should be on pretty much any of them. Okay. Any questions while we're waiting for a minute or two to get people all up to speed and have everything open? Yeah. Don't worry about that. Just click OK. I'm also working with OTS on that. All right. So everyone doing well with the class so far? Cool. Any questions on anything? Yeah.
Will this one require like the lab report write-up they talked about to like take care of that?
Yes. So all the ones where so not the one we're doing in class, the one you do on your own, which will be very similar to the one we are doing in class here. So yeah. You can just press OK to that. I'm working with OTS on that. It's supposed to flip over to the new one after that, but you know, it goes and freaks you out for a month beforehand. Okay, anyone still need another minute or two? Sorry? Okay, let's, oh, I think I see one that's taking a bit still. Okay, so first thing we want to do is we want to make ourselves a new file to work in SAP 2000. So to do that, we'll go up to the top left here, click File, and we'll go and create a new model here. So we'll click on that. You can also click on the little button right under that, does the same thing. Control N is the shortcut that does the same thing as well. And we'll think about it for a second. Okay, and when it's done that, it's going to have this new model dialog open up here. And this is where we set up our model. So the first thing we're going to do is we are going to set the units we're working in. So if you remember from the lab report here, it said we want to be working in pounds, feet, and Fahrenheit. So those are the USCS units that we want to be working in. And you see by default right here, it's set to kips, inches, and Fahrenheit. So let's switch that over in the drop down to pounds, feet, and Fahrenheit here. So pounds and feet, that's pretty obvious. Why do you think we'd want to specify what temperature system we're using? Any ideas? They can, yeah. So SAP 2000 also can consider thermal expansion and the forces and deformations that occur due to that. We're not going to be touching that in this lab because that's kind of advanced stuff, but the options are there. So we've got pounds, feet, and Fahrenheit. And then down here are a whole bunch of different templates we can use to go and generate a model. Now, you might think, hey, we're doing a 2D truss. There's a 2D truss template here. We're not going to click on that one because the way the truss is generated in that template is different from the one we have drawn in our lab report here. In this one here, we want to have these kind of this setup of all the chords here, and the template trusses give us different types of trusses. So instead, what we're going to do is we're going to click on the grid only template right here. So we'll click on grid only, and that's going to bring up the quick grid lines. And this is kind of similar to how in Revit, when you can go and lay out a column grid and stuff and have all your different elevations. This is similar to that, where it gives us kind of this 3D grid of snapping points and grid lines that we can snap our members to. So it's really convenient for drawing stuff like that. So the first thing we need to define is the number of grid lines we have in each direction. So we can define them in the X, Y, and Z direction. SAP 2000 is a 3D program, so it can handle both 2D analysis and 3D analysis. First couple analyses we're going to be doing in 2 dimensions. So the dimensions that we use in 2D are X along the horizontal part of the screen and Z along the vertical part of the screen. And then Y, the Y dimension, would be going into your screen. So that's the coordinate system we work with in the program here. So X is going to be going horizontal and Z is going to be going vertical. Now, if we look at our truss here, how many grid lines are we going to need to define all of the nodes in this truss? So the number of grid lines horizontally we need, let's see, yep. We'd need 1 to pass through all of the nodes in the truss here that we want. So we need 1 through A, another one through B and F, another one through C and G, another one through D and H, and another one through E. So we need 5 grid lines going in the X direction there, or offset in the X direction there. So we will set this first one to 5. Y direction, that's in and out of the screen. We want everything to be in a single plane. So we just need to set this to 1. So everything will be on a single plane there. And then the Z direction, we need lines going up this way in the Z direction. We have one that goes through the bottom chord there, and the one that goes through the top chord there. So we only need 2 in that one. So in the program, we will put in 2 there. Any questions on why we have those numbers there? Make sense? Okay, cool. So the next thing we want is the spacing. So this is how far apart the grid lines are in each of the directions. So in the X direction, that's going to be the spacing between A and B and C and C and D and E. Now, in the simple one that we're doing, all of these spacings need to be the same, but that's okay because that's the structure we're working with here. So what's the spacing here? It's going to be 10 feet. Now, if you remember, we went and set our units, and that's showing up in the bottom right-hand corner here as pounds, feet, and Fahrenheit. So these are in units of feet. So we'll put in 10 feet for the separation in the X direction. Y, we only have one grid line, so it does not matter what you put in there. We can just put in 10 to be consistent. And then in the Z direction, we also have that being 10 feet tall. So there, we'll put that as 10 feet. Make sense? Okay, and then finally, the first grid line location. This is basically just where we want our point of origin to be. 0, 0, 0. I just leave it at that. Keeps it nice and easy. So I've got 5, 1, 2, 10, 10, 10, 0, 0, 0. Make sense? Okay, any questions on this? So we'll press OK there. And then what it's going to do is it's going to open up two windows like this. This first one is an XY plane at Z equals 10. So this is like a plan view of our structure in 3D. Then we've got a 3D view of these grid lines that we just defined. So neither of these are really super helpful for this view that we're presented here. So what we can do to get to this view here is we can go in our XY plane here and go up to one of these buttons here. And we can press the XZ view. And this will give us kind of the elevation view in the XZ plane. So up here in all these buttons on the toolbar, we press XZ, and that will switch this view to the XZ plane at Y equals 0. Now, it doesn't matter if you keep both of these open while you're working. So you guys can have a little bit of a bigger picture to see what I'm doing. I'm going to close the 3D view one right here. So y'all can just focus on the big one right here. Okay, so now we have these grid lines. And you notice when I hover over the intersections here, it's telling me I have a grid point there. So I can go and snap members between all of these grid points and go and draw my truss now. So we are going to draw a truss like this. So the way we do that is on the left-hand side here, we've got all of these tools. There's a line one, it's like the fourth one down. It's called Draw Frame / Cable. So we'll click on that, and it brings us this menu. I'm going to come back to these options later, so I can teach you about all of them individually. So I'm just going to close that out for right now. And we see we have an arrow that's pointing up. Now this means we're in the drawing tool right now. So the way we draw members is we left click where we want to start it, and it's going to be drawing a member to where we left click again. So I started there, and then I clicked here, and it drew that member. Now we see it's still going, so we can draw many members kind of in series here. So the next one I can do, I can click here, and then I can go and click here. But now I'm not really anywhere super useful where I can click another one. So how to get out of this, we can right click to stay in the drawing tool, or we can press escape to just completely get out of it. So if I press escape, that took me out of the drawing tool. We're back to the regular pointer. I can click it again, and we're back into it. Okay, now we want to finish drawing the truss here. Now say we accidentally misclicked and we've got a random member there that we don't want. What we can do is we can click on the member there, and we can press delete to get rid of it. Okay, and then another thing I want to make sure y'all are aware of is when we have a bunch of members that are kind of like we want one here and then we want another one here, we don't just want to draw all the way to the end here. Because we have members that are going to connect at this point here, like this vertical member right here, we can't just draw straight from F to H. We need to draw from F to G and then from G to H. Because of the way the connections work out in the program and what we're going to talk about in a minute, we need to make sure we draw from each node to its next connection. We can't just skip over them. We can't just say F, G, H is all one piece and A, B, C, D, E is another piece. That won't get us the behavior we're looking for in this analysis. So what we're going to do is just click on each of them as we go, and that goes and creates these nodes at each of the intermediate points here. Because if we just go from one end to the other, that doesn't create these intermediate nodes, and that's going to give us a different type of problem. Okay. Any questions on drawing your truss like that? Okay. Now be careful. We definitely want to make sure we include all of our vertical members here. They are on the grid lines, so just double check you included all of them. If you don't, that will change how the analysis is run as well. So we want to make sure those are included. Okay, so this is all of the geometric layout of the truss here. So next thing we need to do is we need to tell the program what each of these elements right here are. So we want to tell them, hey, this is an HSS 2x2x1/4 piece of steel. So the way we do that is we need to go and define in the program what an HSS 2x2x1/4 piece of steel is. Now, thankfully, because people use these structural shapes a whole lot, they've developed whole databases full of all of the standard structural shapes. So we're going to import the HSS 2x2x1/4 shape and assign it's going to have its material, and then we're going to assign it to all of these members here. So to do that, we go to define, and then the second option here, section properties. And then in this menu here, we want to click on frame sections. So it's the one with little I-beam figures there. Everyone good with that? Okay. Now in here, we have fsec1. Now this is kind of a default section. So this is what happens when you go and draw in a shape in your program and it doesn't know what it is. So it's going to give you a default shape. So it has some geometric properties to work with. Now, this is just an arbitrary eye shape, I'm pretty sure. So that's very different than the one we want to use. So we're going to want to import a new property. Now, as we said, an HSS 2x2x1/4 is a piece of tube steel here. So it's the square tube. We'll click on this shape here, and then it's going to bring up a menu. And in here, we want to select the correct database. So we'll scroll down, and the file we want is AISC15.pro. So this is the 15th edition of the AISC shapes database. This has all the cross-sectional properties of all of the steel elements that AISC uses. Now, you'll see there's a whole bunch of these. There's 13, 14, 15. These are for the different editions. For all the shapes we're using, they're going to be in all of these. But I'd recommend using the latest one you have access to. If you're ever using version 15 that we have in the VCL as well, that only goes up to version 14 because that version was before they released the 15th edition manual. So we're going to want to use AISC 15 here because it's the latest as of now. Also, you might notice there's an AISC 15M. Those are for the SI dimensions of all the shapes. So that's in like millimeters and stuff like that. Make sure you're in 15 because this one's not going to have the right shapes for you. So AISC 15, we'll open that up. And then we see we've got all of the HSS shapes in here. There's a lot of them. And there's going to be even more soon. So what we want to do is we want to scroll through and look for HSS 2x2x1/4. And that one is going to be right here. So it's just below the first page there. So it should be HSS 2x2x0.250. Everyone find that all right? So once we have that selected, we press OK. Then it brings up a screen here, and this shows us the cross-sectional properties. So like how tall it is, how wide it is, the flange and wall thickness of the tube here. And it also gives us the material down here. Now by default, because we're importing a steel section, it's given us a steel material. So it's given us A992 FY50 steel. Now this is the material we want to be using. It's just the material we're going to be using throughout the lab. So this is where you'd go to change it if you wanted to. We're not going to be doing that for the purposes of this lab. So we'll press OK. Nothing changed there. And now we have imported HSS 2x2 by a quarter here. And we'll press OK. So that's imported it, but now we need to assign it to all of the members here. So we can select all the members here. It's just like the AutoCAD rules for selecting here. Clicking and dragging right will select everything that is fully within the selection box. And if you click and drag left, that selects everything the selection box touches. You'll notice we've got these kind of dashes along the members here and these X's on the nodes here. So that means it's selected. When we're assigning things to members or assigning things to nodes, it doesn't matter if you select both of them because it'll only assign the properties to a member or a node respectively. So we're assigning things to members now. It doesn't matter that we also have all the nodes selected here. And if you're ever curious about how many things you selected, it'll tell you in the bottom left here. So I've got 8 points and 13 frames selected right now. Okay, so we've got them all selected. You can also press Control-A. That selects everything in the model. And what we're going to do is we're going to go to Assign. Then we're going to go to Frame. And then the first option here is Frame Sections. And that's going to let us assign a cross-sectional property or a cross-sectional shape to each of these frame elements here. So we'll go and click on the HSS 2x2 by quarter that we imported earlier, and then press OK. And once we've done that, now we'll see that on each of the members in our structure here, it says HSS 2x2 by a quarter. Make sense? Okay, so two more things we need to do geometrically. The first, which is the most regular thing we need to do, is we need to assign ourselves boundary conditions. So the structure knows how it's anchored to the ground. So if we recall from our figure here, we want a pin on point E and we want a roller on point A. And the way we do that is we go and select our joint. So go and select point E over here. We see it's got the little X for the selection there. Just click on it. And then we're going to go to Assign, and then Joint, and then Restraints. Everyone got that? Assign Joint Restraints. And that will bring up the Assign Joint Restraints box right here. Now, a boundary condition is going to restrict movement in certain ways. So a pin will restrict it in all three directions. Roller is only going to restrict it up and down. A fixed condition is going to restrict movement in all three directions, as well as rotation in all three directions. And you can also have all sorts of other subspecialty connections with like sliders, stuff like that. That can be other combinations of these. So what you can do is you can go and check off these different types of translation and rotations that you want it to restrain. Though most of the time, we just want to use these fast restraints down here for like fixed connections, pinned connections, roller connections, or no restraint if you want to remove a restraint from a node. So we want a pin connection here. So we're going to click on that. And when we click on these here, you see it changes what boxes are checked on top here. So for a pin, it's going to restrict translation in every direction. And we'll press OK there. And we see we have a pin here now. It gives us a little triangle. That's the pin symbol. Okay, let's go and select this point right here. We want to put a roller there. So we're going to go to Assign, Joint Restraints. We're going to use the little roller quick restraint here. And we see that it changed it to only select translation in the third direction, which is Z. So it's only going to stop movement going up and down here, which is what a roller does. But it can rotate there in any direction, and it can move in and out of plane. So we'll press OK there, and we have this almost circle there. So that's the roller symbol. Okay, now one final thing we need to do for a truss structure here. Now, I'm sure y'all have done trusses a bit in, what was that, statics and mechanics of material a bit. What do you remember from trusses? Anything special about how they're put together? Triangles, they do help, yeah. Why do we need a triangle in a truss? Sorry? Yeah.
The joints are all.
Exactly. So all of the joints are free to rotate. So this is called an internal hinge. So usually I'll just reserve pin for the boundary condition, and all these internal ones I'll call hinges. So all the joints here need to be hinged. Now, by default, SAP 2000 assumes every joint is fixed. But to add these hinges, we need to do that to actually get the correct truss behavior. Otherwise, it's just basically a pseudo beam otherwise. So the way we do that is we need to go and release some rotational constraints in each of these members here. So we're going to select all of the members here. Then we're going to go to Assign. And then we're going to go to Frame. And then we're going to go to Releases/partial fixity. Everyone got that? Okay. Now, what we want to do here is we want to check these bottom 4 boxes. So what this is doing is at each end of all the members we have selected, it's going to not transmit any moment across the connection in our major direction or our minor direction. So that's the same behavior as an internal hinge. You can't have any moment crossing an internal hinge. Oh. Sorry, just a second. Okay, so in lab right now. Teacher. Yeah, I can call you back. Sorry. So in both the major and minor directions, we don't want any moment going across it. So it's basically just modeled as a hinge in 2D or a ball and socket in 3D. So press OK there. And we see that we have these little green circles at the start and end of all of the members here. Now that means we've successfully released all of the rotational constraints at each of our nodes there. Make sense? So there's an easier way to do this, like when we're drawing here and we have this member here. Moment releases, we can change this to pinned instead of continuous. And as we draw it, that'll include those moment releases as we go. And we can also say what section we want as we're going there, but we have to have imported it first. So that's a faster way to do it instead of having to go back and assign the section, go back to assign the pins. But it's good to know what we're talking about before we get into everything too deeply. So that's another way to do all this. Okay, so now we've finally defined all of the geometry. We have the whole layout, we have the cross section, we have the material, we have the boundary conditions, and we've also included the special moment releases for a truss. Okay, so that's the geometric side. Now we need to add forces. So we need to add our loads. So the way that's going to be, we need a 50-pound force at this joint here and a 100-pound force at this joint here. Okay, so we are going to select this one right here first. And to assign a force, we're going to go to assign. We're going to go down to joint loads, and we're going to click forces. Everyone got that? Okay, so in here, we've got a couple options at the top. Those are fine for now. And here we've got a whole bunch of boxes we can click to assign forces in the global X, Y, and Z direction and moments about the global X, Y, and Z axes. So we don't need to assign any moments. We just want to assign a 50-pound force going to the right here. Now, if we look at our coordinate system here, our positive X is going in the same direction as we want that load to go. So we're going to put in a positive 50 for our force global X box here. Now recall we're in pounds, so it's got it designated there and in the bottom right here. So those are the units for the force we want to apply. At the bottom here, we don't need to worry about that. That just controls what happens if there's already a force there and you want to assign another force to that node. In this case, it would replace the existing force. We don't need to worry about this for this one though. So we're just going to press OK there. And now we have a 50-pound force applied to our node here. Make sense? Okay, we're going to do the same thing for this one right here. So we're going to go to assign, joint loads, forces. Now, we see that the 50 stayed from last time, so we want to make sure to set that back to 0 because we don't also want a 50-pound force there in this case. And what we want to do is we want to have a 100-pound force going downwards. So if we look at our coordinate system, we see that the vertical axis is Z, but it's pointing up. So to go downwards, we're going to need to put it as a negative. So we're going to put in negative 100 here in the force global Z box. Make sense? Okay, then we'll press OK here. Now we have the 50-pound force here and the 100-pound force here. We've applied all of our forces. Okay. Any questions on this? So now we can run our analysis. So we can go to either analyze up here and do a bunch of stuff here. The easy way to do it is just use this triangle button on the hotbar here. So it says run analysis. You can also press F5, that's the shortcut. And that will bring up the set load cases to run menu. Now in here, we have a couple load cases. The dead load case, which is the type of loads we've applied to our truss here. Oh, I also remember I just forgot one thing with loads. Let me do that before we get to this. So we applied all of our forces, but we forgot to turn off the global forces, or we forgot to turn off the self-weight of all of these HSS pieces here. So the way we do that is we go to define, define. Then we go to load patterns here. And here, this is the dead load case. This is the types of loads we're applying to our structure. And the self-weight is default applied to the dead loads here. Now, we have it selected in our table down here. And what we want to do is we want to set the self-weight multiplier to 0. So this goes and basically just zeroes out all of the self-weight loads that the program wants to apply to the structure automatically. So we'll put in 0 there. And then on the right here, we're going to say modify load pattern so that it updates it in the table down here. When we have a bunch of different types of loads, you'll see makes a list down here. But we don't need to do that for a couple labs. So we set that to 0 first, and then we press OK. Sorry about that. Now we can run the analysis. So we'll run the analysis. We've got the two types of loads here. Dead load we want to run, modal loads. That is for a dynamic analysis. Out of the scope of what we want to be doing. Doesn't take too long, especially on a nice computer, but the bigger your structure is, the longer it can take. So usually I just go and turn that off so we don't spend a bunch of time running an analysis we don't need. Okay, so we go and click this button up here, say that says run/do not run case. This basically just toggles if it's going to run an analysis or not for that specific load case. We will click run now. And then because we haven't saved it yet, it's going to want us to save it somewhere. Now, when you're saving a analysis file like this, SAP2000 likes to make a lot of files when you run an analysis. It makes like 20 of them. So what I usually do is I'll go and make myself a new folder for each analysis I run to go and keep all the files somewhere together, because it just makes your folders just an absolute mess if you don't. So I'll call this lab 1. Name your lab. And then save it in that new folder you made. And then it'll run after you've saved it. Okay, this will give you some messages here. As long as it ran, it's fine. So we're just going to click done there. And it should give you something that looks like this. Okay, any questions so far? Okay, so we've run our Truss structure now. Now what we want to do is we want to look at some of the deliverables that we're going to want to include for our report. So the first one is the reactions for each support with values and arrows. So how do we get the reactions here? So this initially defaults to the deformed shape. Let's get to reactions. So to do that, we go to display. Then we go down to show forces and stresses. And then we go to joints. So we'll go and click on that. We can also use F7 as a shortcut to get to reactions. And it's going to ask us what type of reactions we want to see. We want to see them for our dead load case because that's the only one we have. So don't worry about that. And then the type we want to display, just keep it on arrows. And then we can press OK. So this will give us our reactions here. So we've got 50, 62.5, and then 37.5 here. Any questions on that? Okay, so in your report, when you're doing this for your practice problem, you can just go and take like a screen grab of the truss here, make sure I can read the numbers there, and include that for your deliverable for the first one there. Make sense? Okay, so the next one we want to see is going to be the axial force in each member, showing the values. So to do that, we can go to display, and then show forces and stresses. And then down here in frames, cables, and tendons. You can also press F8 to get to this menu. And there's a good number of options here. What we're going to work on here is in this component here. So by default, it's selected axial for us, and that's the one we want. And then down here, we don't need to worry about scaling. And then down here for options for diagram, it defaults to fill diagram. That doesn't give you any numbers though, unless you hover over it. So we want to click on show values because that'll give you the max values for each of the members there, or the extreme values for the members, sorry. And then we can press OK. And that will show us the axial forces in each of the truss members. So the red ones here are in compression. The blue ones here are in tension. If you hover along the numbers here, that will go and give you the axial force as a function of the position. You can also kind of read that from the little graphs that's plotted here. Here, not too bad. If you want, there's a button up here called object shrink toggle you can click that goes and shrinks them a little bit to help you. That doesn't work quite as well in this version. It shrinks them a little bit to make it a little easier to read. And there's the numbers there. So you can go and take a screenshot of this for the axial. Make sense? Okay, the next one we want is the deformed shape. So we default, that showed up on the default here. So the way we can get to that is we can go to display, show deformed shape. Shortcut there is F6. And we have a whole bunch of options we can use here. Usually the only one I change here is to turn on wire shadow, because that will give you an undeformed kind of outline of the structure in the background. And the nice colorful one in the foreground will be the deformed one. It gives you something to compare it against to see how it deformed. So we will press OK here. And now we have the deformed configuration in blue and the undeformed configuration in gray in the background there. Make sense? Okay. The next deliverable, real quick here, the horizontal and vertical displacements of joint H. So joint H is this top right one here. The way we can get those is we can kind of hover over the deformed shape here. We see we're hovering over this deformed node right here. And it's giving us some information when we hover over it. So it's giving you the point object and the point element IDs. And then it's also giving you some U values and some R values. So U1, U2, U3 are your displacements in the X, Y, and Z direction. And then R1, R2, and R3 are your rotations about the X, Y, and Z axes. So displacements and rotations. And our horizontal displacement is going to be U1, and our vertical displacement is going to be U3 there. So we'd go and record down those values. So you can either right click on this to go and get this little menu that pops up here for joint displacements that has these values in it. So that's easy to screenshot, or you can just write them down in your Word doc or whatever. And that works for me too. Any questions on these? Okay, and then for the last deliverable, stresses. And then we go to frames, cables, tendons. And then here we go and click on the moment 3.3, then press OK. And what it's given us is a diagram with no moments on it. And that is exactly what we are looking for in this case. So because we have a truss structure and it's jointed at every single node, and it can't transfer moments between those nodes, and we're not applying any forces on the members themselves, only at the joints, that goes and imposes that the only forces in the members can be axial forces. So there's no bending going on in any of these members here. That's why we really like trusses, because we only have to analyze the axial force, and we don't have to worry about bending or shear or torsion or any of that other junk. So that makes truss analysis really easy, because there's no moment in it. In reality, there's a little bit because of self-weight and stuff like that. Loads aren't perfectly on joints, but it's pretty close. So we want to check the moment here just to make sure that we got everything right. And if there's no moment diagram here, we didn't mess anything up. Now, if you are getting a moment diagram, the two common things that I usually check to see if I accidentally missed them is forgetting to turn off self-weight or forgetting to release the joints, release the moment at each of the joints. If we forget to do either of those, that'll go and give us some moment diagram here. Okay, so that's the analysis I did today. Sorry, I think I went just too on time here. If you guys have any questions on this, please let me know. Yeah.
Sorry, there were a couple of my joints I forgot to set.
Okay, so first, after we've run an analysis here, we see it's locked here in this option right here. So what we want to do is we want to click on that to unlock it. So that goes and throws out the analysis results, because if you're changing the model, it's going to give you new analysis results. Go and click on that. And then what we do is we go and select all the members you want to release your ends on. So in our case, all of them. So we'll select all of those. Then we'll go to assign, frame, releases / partial fixity. And then in this one, we go and check the bottom 4 boxes there. And then press OK. Does that work for you? Interesting. Maybe you didn't turn off your self-weight. Any other questions? So this one in class was an example. I believe right about now, the assignment I have that corresponds to this lab went live on Blackboard. So if you look at that, that's going to be a truss pretty similar to the one we did in class. And you'll go and do the deliverables it asks for. I think it's the same ones we did in class. And then you'll go and write your lab report on that. Sorry, what did it? Oh no, don't worry. This one's kind of hard to remember unless you do it a bunch. Go to assign, frame.
As I need to frame.
Right. Well, it's an attribute that gets applied to the frame element. It's how you do it in the math in the background. It's a little weird. Any other questions? All right. So thanks for coming to lab. Let me know if you need any help.